The Portal games have several hidden rooms, often filled with cryptic messages or mysterious drawings, hinting at what's going on in the Aperture facility. While most of these Easter eggs have already been found, not all of them have been thoroughly investigated and put into context. And while replaying Portal 2 recently, I came across one of these rooms that I found particularly interesting, as someone who has a background in physics. In this room, you'll find all of these equations, and other than a convoluted thread on Reddit, I can't find any other description that dives into them. So I thought it would be fun to make a video dissecting what we see here, and talk about how these equations might relate to portals in the game, and just some generally spooky aspects of physics. Before we get to the equations, let's address the cat. In the physics of quantum mechanics, we run into situations of duality. Things may be in a superposition between two different states. Sometimes particles behave like particles, other times like waves, all depending on how you interact with or observe a system. The double slit experiment is a good example of this. Send particles through two slits. If there is no detector interacting with them as they pass through the slits, then they will behave like waves and form an interference pattern. If the particles are observed, however, they will pile up in two locations corresponding with each slit. So what are they? Particles or waves? It's dependent on detection. The state of a particle may actually be in a superposition between states until a detection is made. So an idea that Schrödinger came up with is that by attaching some quantum system to a poison inside of a box, and then putting a cat in that box, the cat is in a superposition between life and death until we open the box, famously known as Schrödinger's cat. This is a portal cat though, so it can just portal out of the box. Also, just beneath him is a little Easter egg for the final boss fight. Moving on to the next equation, at the top here we have the time-dependent Schrödinger equation. The letter psi here, which looks like a little trident or a pitchfork, is a wave function, just like how we talked about particles acting like waves. The wave function is a pretty big deal in physics, as it can mathematically tell us a lot about a system. And the square of the wave function is related to the probability of finding it in some state, which we can actually measure in a lab. The equation relates the energy of a system to the wave function that varies over both time and space. Even though it looks a little scary, all that it's saying from left to right is total energy is equal to the kinetic energy plus the potential energy. The reason it looks so complicated is all the other stuff is related to operators. So we have a total energy operator, a kinetic energy operator, and a potential energy operator. And I bring this up because the next equation is another operator. It's the momentum operator acting on the wave function. I'm not sure why they have it equal to E psi, because we normally use the letter P for momentum in physics. But at the end of the day, this is still a video game, so maybe that was a typo. There's another place on here that we see momentum, which is off to the left in the Heisenberg uncertainty principle. This equation says that there's a minimum amount of information that you can have about a system's position and momentum, and the more you know about one, the less you must know about the other. Think of taking a picture of something while it's moving. It might be blurry, which means you don't know much about its position, but it does tell you something about its momentum. Say you speed up your camera shutter and get a clearer picture. You now know its position very precisely, but you no longer know anything about its momentum. This can lead to all kinds of quantum weirdness, especially with another version of the uncertainty principle, but that one uses energy and time. That's a nice transition to our next equation. This is time dilation from special relativity. It's really quite amazing how simple it is to derive this equation. Basically, if you assume that the laws of physics are the same for everybody, that the speed of light is constant, and if you know the Pythagorean theorem, then you can derive this equation which says that time slows down for an observer moving relative to another. I have another video about relativity, which I really put this into its simplest terms, but then use it to show how a straight line is unintuitively the longest path through space-time. I'll leave a link to it at the end of this video. I have another video in the works which combines this principle with wormholes, which share some similarities with portals, and that'll show how moving wormholes and time dilation actually allow for time travel to the past. That's going to be a very interesting and trippy video, so if you're interested, make sure to subscribe to the channel and hit the bell icon so you don't miss it. Alright, we're almost done with these equations, and I'll make the last ones pretty quick. You see this one right here? We're not going to talk about it. I recognize some things from Maxwell's equations for electricity and magnetism, but it looks pretty messy and not entirely correct. Even if I did start talking about E&M, this video would be a lot longer. This last one brings us back to quantum mechanics, with an equation that is a little hard to read, but appears to be an application of the Schrödinger equation for some potential dependent on position r. The potential can be thought of like a dip or a well, and the Schrödinger equation can tell us how this well impacts the wave function and the probabilities we might get as a result. Now, you'd think when encountering a part of the well that our particle doesn't have enough energy to overcome and get out of, that it would remain stuck in the well. But this isn't always the case. Some of the wave function actually can propagate through the wall, and the particle can quantum tunnel to the other side. This going through one wall and coming out the other sounds awfully familiar, and might be a little bit of the science in the science fiction behind portals. Matt O'Dowd from the PBS Spacetime channel has talked about the chance of a human quantum tunneling somewhere other than where you are right now. Now, it's unlikely, but he says, "You're everywhere in the universe, but not very much. You're as right there as it's possible to be." I'll leave a link to that video down in the description. It's very interesting. In it, he also mentions there's an infinitesimal chance you're actually on the moon right now.